Hello and welcome. Thank you for coming. My name is Pedro Paez, and I'm a specialist solutions architect for machine learning and artificial intelligence here at AWS. I'm based here in Singapore. Okay, and today what we're going to do is we're going to discuss how you can build, train, and deploy deep learning models on Amazon SageMaker. Okay, now Amazon SageMaker is our machine learning platform, and we'll get into the details of how that works later on this slide. Okay. Now, just to give you an overview of what we're going to discuss today, we're going to start with some theory around deep learning models, how they work, and why are they such a buzzword now. Okay. We are going to follow that up with some deep dives on Amazon SageMaker and our ML services. And we will finish with a demo of building some really interesting use cases around computer vision, all using SageMaker. Okay. Before we start, I'd like to invite you to the rest of the breakout sessions on this ML track. And if you're not able to see them live, please go look for them whenever they're available as recordings. So let's start with a little theory around deep learning. Normally, when we talk about deep learning, we also talk about machine learning, right? And deep learning is actually just a subset of machine learning. Okay, and what is machine learning? If you think about the traditional computational paradigm, what we traditionally did was we were pre-configuring some functions, embedding these functions into a computational system. The system would normally expect an input, and then we as users would expect an output from the system, right? So think about calculators, right? Calculators have the function square root embedded in the calculator. The calculator expects a number from us, so let's say number 16, and then we expect a value returned, right? So let's say number 4, right? 16 and 4 square root. With machine learning, we're actually going to turn this paradigm on its head. And what we're going to say is, instead of me giving you the function, I am going to give you a bunch of examples of inputs and outputs, x's and y's. And I want the computer to learn to infer the underlying functional relationship between these x's and y's, inputs and outputs, okay? So here's an example. Here we have two populations, two sets of data points, blue population and red population, right? And normally what we're trying to do in the traditional problem, now this is a more basic problem that we do in machine learning, is to try to discriminate between these two classes, okay? We're going to try to find a model that's able to discriminate between the population blue and population red. So normally what we do is we have a nice little simple function here in this specific use case. It's going to be a straight function. This is what we call a linear function that is going to be we're going to learn using these data points, okay? And what we're going to be able to do with this function is later be able to infer on and extrapolate on other types of data what represents a blue dot and what represents a red dot. Okay, so let's take as an example sentiment analysis. Okay, so normally you've heard about this. You want to do sentiment analysis on tweets. What we have is historical data in this example. Let's say the blue population represents positive sentiment tweets, and the red population represents negative sentiment tweets. Okay, and here we find a nice linear function that is going to help us, that this is going to be our model to determine whether a tweet is positive or negative. Okay, so now when we have a new tweet or a new data point, if the tweet falls on the right side of the line, we say that it's a positive sentiment tweet. And if it falls on the left side of the line, we say that it's a negative sentiment tweet. Okay, and we can do the same thing with computer vision, images, right? So let's say we want to create a model that's capable of detecting from images whether the image is an image of a cat or an image of a dog. So again, we have historical data. Blue population represents our historical data of cats. Red population represents our historical data of dogs. We create a model, nice simple linear model. Whenever we have an image that falls on the right side, it's a cat. If it falls on the left side, we say it's a dog. Okay? But most real life problems aren't this simple. Okay? Most real life problems, including this computer vision cats and dogs problem, are very high dimensional, very complex, very nonlinear problems. Okay, and just again, there's a explicit definition, mathematical definition of what linear and nonlinear is. But for layman's terms, linear is usually simple, nice, and pretty, and nonlinear is complex. Okay, so here we have another example of a nonlinear problem. It's the exact same problem we had before, two populations, red and blue, except in this case, we can't really draw a nice linear function to separate our two classes, right? Now, there are many ways of actually transforming this data to get a linear problem, okay? One of the ways is actually doing an explicit transformation. Here, what I've done is used something called transformation for going between a Cartesian coordinate space to a polar coordinate space. And what you can see is, once I've done the transformation, now I can draw a simple line down the middle, and I have my separation between blue and red, right? Now, in real life, like I said, this is a toy example. Most problems are going to be high-dimensional, very complex, very nonlinear, and very tangled, okay? And the idea is that we want to transform these very nonlinear, complex problems into linear, simple problems, okay? And that's what deep learning is actually really good at. So what is deep learning? Deep learning is inspired by biological learning, okay? So think about the brain, right? This is a very high-level analogy. The brain, you can think of the brain as clusters of neurons, right? And neurons are just simple functional units. They receive an input, and they react accordingly, okay? So what's interesting about this cluster of neurons is that when we aggregate or stack a lot of neurons together in a specific configuration, the brain is able to understand or learn very complex tasks, right? So humans are able to learn new languages, learn art, learn quantum physics, for example, right? And this is all kind of just derived from this very simple functional unit. So what we're going to try to do with deep learning is we're going to try to emulate that. Our simple functional unit is going to be called a perceptron, and we're going to stack a bunch of perceptrons together in the hopes of finding very complex tasks. So this is a traditional deep learning architecture, okay? We go from left to right. The leftmost layer is what we call the input layer. This is where our input data is going to come in. This can be images, text, sound bites, numerical data. We're going to push that data from left to right. It's going to flow through this middle layer, which is called the hidden layer. And this is actually where our stacked perceptrons are going to be. These stacked perceptrons are going to transform our data, as we did before, from a very complex, high-dimensional space to hopefully a more nice, simple space where finally in the output layer, we will be able to make a nice, simple decision like a linear decision, right? And this is what we call the last output data is going to be the discriminator, okay? So initially, actually, these models are very dumb, okay? These models are actually initiated as random weights. So how do we learn? We go from this dumb model to a very performant, complex model, okay? This is actually something that we call statistical learning. And this is the basis of machine learning, okay? So how does statistical learning look for deep learning? So as we see here, we have this input data, which is going to be very high-dimensional, very complex data. It's going to flow from left to right through our network of stacked perceptrons until finally, at the end, we make a decision, okay? Now, this can be initiated, again, randomly, right? So the transformations aren't good at this point. We make a decision, is this a cat or a dog? If we make an error, then we are going to reevaluate our model. We're going to change these model weights. And this is something that we call backpropagation with deep learning. Okay, so we reevaluate our weights, and then we start all over. And this is the iterative process of, with new examples, learning to change our model. And this is what we call, again, statistical learning. Okay? But again, some general concepts of this process. Neural networks in general, under certain configurations, this is a mathematical result, are general function approximators. So we're able to learn a whole tasks of different types of functions, okay? But they are very complex to train, okay? And the training process is something that in mathematics we call optimization problem. And this is actually something that's, in the most part, a non-convex optimization problem. And what this means is that it's going to be very hard to find an optimal solution. And when it's hard to find an optimal solution, that means that this is going to be a computationally intensive task, okay? And that's why we can't really separate all the mathematics and statistical nuances of creating deep learning models from the resources required to actually train the model, okay? The difference between using a GPU and a CPU is going to be the difference between training a model in a week and training a model in a couple of hours. So that's where we come to AWS. So let's talk about AWS's approach to machine learning and deep learning. This is what we call the three-layered approach. Okay, so this is a map of our services. We call it a three-layer approach because we're separating our services into 3 layers, okay, going from bottom to top. Our first layer is our ML frameworks and infrastructure layer. So the center of this is going to be our deep learning AMIs. So these are basically elastic compute instances that have already been pre-configured with all of the necessary deep learning frameworks, CUDA drivers, GPU power for building deep learning applications. Okay, there are some really nice innovations coming out of re:Invent, including elastic inference. These are very specific to inference and to infrastructure. And for example, our EC2 C5 instances, which are compute optimized instances that use Intel Xeon processors for doing a lot of the hard work. Okay, so a lot of innovations also coming out around the infrastructure side. Now, when we want to build our end-to-end data science workflows, and we don't want to have to deal with all of the infrastructure management that requires, we come to the second layer. And the second layer is basically our ML services, and the center of this, the heart of this, is going to be Amazon SageMaker. Okay, and we'll discuss Amazon SageMaker in a little bit. And then our higher level service, so this is our third layer, is what we call our AI services. Okay, and our AI services are basically out-of-the-box API services for doing things like computer vision, natural language processing, building recommendation engines. Okay, and this is going to be really nice because you're going to get out-of-the-box really sophisticated deep learning technology. Okay, that you can embed into your applications with little to no data science experience. Now, if your use case doesn't fit into one of these pre-configured models or use cases, then you're probably going to have to be looking at building custom models. Okay? And when we talk about building custom models, that's where we go back to SageMaker. So let's talk about SageMaker. Let's get to SageMaker. There you go. Okay. So let's talk about SageMaker. So again, SageMaker is our end-to-end machine learning platform. Okay. SageMaker, at AWS, we understand that data science is basically made up of 3 tasks: data processing, data exploration, building and training your models, and then how you deploy your models into production. Okay? And we're going to take this philosophy, and at AWS, we also understand that these 3 different tasks also require 3 different types of resources. So you're not going to use the same resources or infrastructure that you need for training a deep learning model, like GPU instances, to do data exploration, right? And you might not even need those GPU instances for deploying your model into production, right? So we're going to decouple these 3 tasks and allocate them their own types of resources, okay? And this is what we're going to be able to manage and orchestrate with SageMaker, okay? So let's talk a little bit about how I can get started with SageMaker, okay? First thing we have, and SageMaker does offer, is something called pre-built notebooks. And these are just going to be a whole catalog of different tutorials on how to build computer vision problems, time series forecasting, using TensorFlow, using MXNet, using Spark. Okay, you can get quickly started with one of these notebook examples. Okay, now let's say I want to build and train a model. How do we leverage SageMaker to build and train models using high-level compute instances? Okay, so there are 3 ways of actually leveraging SageMaker for doing this. First way is using the first-party algorithms. Okay, and the first-party algorithms are just basically pre-configured, pre-packaged, very popular algorithms such as computer vision algorithms, unsupervised learning, time series forecasting that we've already optimized for using out of the box within SageMaker. Okay. Second way of using SageMaker for building your models is by using our high-level SDK for deep learning frameworks or machine learning frameworks. Okay, so what we've done is we've natively embedded, implemented a lot of these popular frameworks such as TensorFlow, MXNet, PyTorch, scikit-learn within SageMaker, so that you're able to leverage all of the really nice features of SageMaker by only bringing your normal TensorFlow or MXNet code, for example. Okay, and the final way of actually leveraging SageMaker is by bringing your own algorithms. Okay, and this process requires a little bit more engineering, but also offers a lot more flexibility. Okay, and the actual engineering involved in this is containerizing, creating a Docker container with your training algorithm. Okay. Before we finish, we also have a nice little feature called automatic hyperparameter tuning. And this is a great feature because it allows customers. So again, think about when you're building deep learning networks, these have a lot of parameters. And it's a really blocker, it's a real big obstacle for data scientists to actually manually fine-tune these parameters, right? So normally there are some schemes for doing this automatically, and SageMaker has implemented a really nice scheme for doing automatic hyperparameter tuning, meaning you get automatically the optimal configuration for your model. Great feature for data scientists. And finally, I have my model. How do I deploy this model? Okay, how do I get this in production? That's where we have this really nice feature called one-click deployment. Okay, what you get here is by a simple API call. You get some really nice vertical and horizontal scalability of the resources needed for deploying that endpoint. Okay, you can deploy your endpoint in production as a RESTful API, and you get some really nice features out of it, such as automatic scaling and A/B testing. Okay, and this is all out of the box. Some really important customers already using SageMaker for building their machine learning and deep learning applications, such as Tinder, Snapchat, Sony, Intuit. Okay. So let's talk about the deep learning frameworks that are supported by AWS. We normally say that AWS is framework agnostic. Okay, and this means that explicitly or implicitly, we do support all of the deep learning frameworks. Now, natively, SageMaker, for example, supports the more popular frameworks like TensorFlow, MXNet, PyTorch, Chainer, Keras. Okay, and this will be out of the box. So why do we talk about TensorFlow? TensorFlow is one of the most popular deep learning frameworks. Okay, a recent study showed that 85% of TensorFlow workloads being run in the cloud are actually being run on AWS. Okay, and another thing is that SageMaker and the deep learning AMIs do support TensorFlow natively. Okay. PyTorch is another very popular deep learning framework. Very popular amongst the research community, especially coming out of things like Facebook research. It's a very versatile framework, and because it is a very popular framework around the research community, there is a really nice story about the transition from research to production using SageMaker with PyTorch, for example. Finally, we have MXNet. MXNet is another very powerful deep learning framework, and we'll actually talk about this during our demo. Okay, so PyTorch has some really nice functionalities and features such as gluon-CB and gluon-NLP libraries, and these are just high-level libraries for doing computer vision and natural language processing, and you can really get accelerated with these type of very advanced functionalities using this type of libraries. Okay, another really interesting about MXNet is that it has a really nice integration with Keras. Okay, and this is really powerful because it allows developers and data scientists to build architectures, to build models with less of the verbosity that is normally associated with these kind of low-level deep learning frameworks. Okay, so let's get started with our demo. Okay, so what we're going to do now is we are going to build two different types of neural networks. This is going to be around computer vision. We're going to use, on one hand, we're going to use one of the first-party algorithms, and we're going to try to build an end-to-end deep learning framework and deploy it in production using the first-party algorithm. And then on the other hand, we're going to make some more complex applications, bringing in some custom code, okay, using MXNet. So let's try to run. So, okay, so this is the AWS console, and we are going to go into SageMaker. So you can see what SageMaker looks like, okay? So this is the SageMaker console. And as you can see, remember I talked about decoupling the three tasks of data science, right? Data exploration, that's what we're represented by the notebooks. Model training, and model deployment. And you actually have access to monitoring and controlling all of the resources that you're deploying within SageMaker in this user interface. Okay, so let's get started. Let's spin up a notebook. So that right now we're going to spin up a project. Just want to show you how this is done. We are going to create a notebook instance. Okay, we are going to call it demo. And what you see here is the vertical scalability of SageMaker, right? We can choose any type of infrastructure for actually building our project. Here we have something called permissions, and permissions is AWS's way of controlling and governing who has access to what resources. And again, as you see here, we have Git integration. So this is great for versioning and for collaboration of data science projects. We're not actually going to use this. What we're going to use is a pre-built project that I did for this demo. And what we're going to do now is we are going to build a cats and dogs computer vision model. Okay, so this is actually the Jupyter Notebook SageMaker interface. Jupyter Notebooks is the tool of choice, very popular within data science community. And what you can see here is that we have pre-configured environments for building things like TensorFlow, MXNet, Spark jobs. Okay, and this is out of the box. You don't have to configure this. An additional thing is that we do have access, so shell control over this instance, meaning that developers and data scientists can bring in any library, any framework they want to use using the shell control, okay? You can create, for example, virtual environments or additional kernels for the Jupyter Notebooks. So let's go back and let's look at our example. So again, this example, what we're trying to do is we're going to try to build a computer vision model that's able to discriminate between cats and dogs. And this is a complex deep learning model, okay? what we're going to do here is we're going to use our first-party algorithm. So this is what how you normally use. You create your projects, data science projects. It's a Jupyter notebook. The first thing we're going to do is we are going to configure the environment. Not a lot of code. Two things we have to do here is define the roles, so the permissions that this notebook has, that this project has. It has access to what types of directories, for example. And we are going to define a directory. And this directory is going to be a bucket in S3, in our simple storage service. Why is this important? Because SageMaker is going to use this direction for orchestrating the training and the deployment of our models. Second thing is we are going to import or invoke our first-party algorithm. In this case, we're going to build an algorithm for doing image classification. Okay, so we're going to invoke a prepackaged, it's actually a Docker container image of image classification algorithm. Okay? Now again, hopefully we'll build this in less than 10 minutes so you can see the results of this. Second thing here, I've already downloaded a data set, and what we are going to give the model is a bunch of images of cats and dogs. Remember the original picture I showed you? We have pictures of cats and dogs, and we want to draw a nice little line between the two to be able to have a model to discriminate between images of cats and images of dogs. Okay? So input data, lots of images of cats and dogs. We have to do a little pre-formatting for the algorithm, and this is just the format, the documentation of the algorithm requires this. We have to give annotation, a text file. Okay, and basically what this says is, give me the name of the file, the name of the image, and tell me what type of class this represents. Okay, so for example, the first image represents a dog, and that's going to be mapped to class number 1. Second image represents a cat, and that's going to be mapped to class 0. Okay, so cats equals dogs equals 1, cats equals 0. And now what we're going to do is we're going to upload our data set to S3. Okay? So we upload our data to S3, and this is where the magic happens in SageMaker. Okay, here in this snippet of code, we are actually encoding all of the vertical and horizontal scalability of SageMaker. So right now what we're going to create is something called an estimator object, and this estimator object is going to allow us to actually build and train a model. We tell it that we're going to use the image classification algorithm, okay? And these two lines are the really powerful lines, okay? In these two lines, we have the encoded vertical and horizontal scalability. First line is going to give us horizontal scalability. How many instances do I want to use to actually train my model? If the model is distributable, then you can actually do distributed training for deep learning models. Okay, you can go from 1 to 10 to 100 by changing that number. Second thing is vertical scalability. Okay, just by changing a parameter in that line, I get to go from CPU instances to working with GPUs. Okay, so right now I'm working locally on a CPU. If I want to use GPU for training deep learning models, that's the parameter I have to change. So right now we are going to use a P instance. P instances are GPU empowered instances. Okay. Now, one of the nice things about this first-party algorithm is that we can use something called transfer learning. And transfer learning is basically you get to use pre-trained models to train your own personal models. And this is nice because you don't have to start from scratch. Okay? Meaning I don't have to use as much data as normally these models require. And also, I can only use 10 epochs. Okay? Normally, these models require hundreds, thousands of epochs to actually train the model. Here, I'm only going to use 10 epochs. Okay? So this is very economical. Okay? Next thing is I'm going to configure the input for my data, tell the model where my input data is and what type of data I'm going to push. And finally, what I'm going to do now is I am going to push this data and call a training job. Okay, so right now I'm going to fit my model with my training data. So what's happening now? SageMaker is orchestrating at this point. Remember that data that we put in S3 for training? Going to need that information. It's going to need the information for the type of algorithm I'm going to use. This is a Docker container. And it's going to need the information for the infrastructure that it wants to build. And what SageMaker is going to do is going to put those ingredients together. It's going to train a model. It's going to output that model into S3. And then it's going to kill all the infrastructure that is spun up. Okay? And this will all be transparent to you. Meaning that SageMaker is managing all of the infrastructure required to spin up and train this model. And you're not seeing any of that. Okay? What you are seeing is the output of this, okay? The iteration process, the learning process of the model through logs. And finally, we're going to have a final model output. And what you can see here, it took 538 seconds to train this model, so that's roughly 10 minutes. And what I'm paying in terms of infrastructure is those 538 seconds. Something that does not happen if I have to spin up that infrastructure myself. Okay, so great. Now I have a model. How do I deploy this model into production? Right? Deploying this model into production is as simple as this one line of code. Okay? And if you see the parameters, again, we get the horizontal and vertical scalability, right? I get to say, how many servers do I want to host my endpoint? That's a parameter here. I can go from 1 to 10 to 100 just by changing the parameter. What type of instances do I want to use? Maybe I don't have to use GPU instances now I use GPUs for training my model. I don't need GPUs for deploying my model, right? I can do that too. Now, we have even more. Now, it's not just that simple. You can always add more granularity to this configuration, adding things like auto-scaling strategies or A/B testing. And now these things come out of the box, okay? So this took a couple of minutes. We've actually deployed a model. And what we have right now is a model being served live as a RESTful API. So again, this is live right now. It's been deployed. This is in production. So what you see here, you have access to your resources. Remember what I said before, you have access to your endpoint, your training, your testing, and deploying resources. And what we see here is the URL for this RESTful API. Okay? So what have I done so far? I've started with data from scratch. I've created a deep learning computer vision model, and I've deployed this model into in production. And I've done it in less than 10 minutes. Okay? So let's test out this endpoint. What we are going to do right now is we're going to look for an image of a puppy or a dog. It's a dog. Actually, I already know that it's a puppy. We're going to grab the first image. Again, it's a puppy. And we are going to push this image to our model. And ideally, our model should have learned that this image represents a dog. So we are all here, everyone here is able to understand that this image is an image of a dog or a puppy. But we want the model is to have learned that this is effectively an image of a dog. So right now, we're just going to download the data set, the image. And we are going to push this image up to the internet where my RESTful API is. I'm going to do a HTTP request. I'm going to do a post request, send my image, and I'm going to get a result. Okay, so let's see what the model has been able to do. Again, we've done this in less than 10 minutes, right? So let's see. Let's get that model, that image into our system, and then we'll push it up into the web. Great, so we have that nice little puppy. And effectively, the model has been able to detect that it's a dog with confidence level of 99%. Okay? So what have we done here? We've built an end-to-end solution within the same platform, used different types of resources, built a very sophisticated computer vision model, all in under 10 minutes. Okay? And this is using the first-party algorithms. Okay? But again, this is a very simple vanilla problem. We can always do more sophisticated, more complex things. And that's what we're going to see next. We are going to build a more complex, more interesting model using something that we call GANs. Okay? So these are generative adversarial networks, very sophisticated models. And we are going to build this using our own algorithms. We're going to bring actually MXNet code. So what we're going to do here is build something we call cycle GANs. And this is inspired on some really interesting research work being done at Berkeley. Okay? And this, the work being done at Berkeley was actually abstracted and implemented in the gluoncb library. And what we've done is I've implemented that gluoncb library information or those gluoncb modules to build that on SageMaker. Okay? And I won't lie, it took me maybe less than 10 minutes to move that MXNet code onto SageMaker. Okay? So the first thing we're going to do, same as before, we configure our environment. We're going to download the data set. And for this specific use case, we're going to see how cycle GANs allow us to go from image of type A to image of type B, and from image of type B to image of type A. So what we're going to learn now are two different types of models. A model that's going to help us transform images of horses into images of zebras, and another model that's going to help us transform images of zebras to images of horses. Okay, that's what cycle GANs do. So here we have, what we're going to feed to the model is a bunch of images of horses and a bunch of images of zebras, and hopefully the model is going to learn to do the transition from one to the other. Again, these are very sophisticated, cutting-edge research problems that have been implemented in nice frameworks such as MXNet. You can do this with TensorFlow as well. Okay, so we have a smiling zebra there. What we are going to do, as we did before, we have our data set. We're going to push this data set into S3. Okay. Why? Because this is kind of the convention that SageMaker uses for building the models. Okay, we've uploaded our data. We are going to give some hyperparameters to give the context to our model. Okay, and then what we're going to do here, again, we have the scalability of our model by using, we can use, especially for this complex problem, we're going to need to use high-level GPUs. So we're invoking a P3 instance for this. Okay, and instead of using the estimator function we did before, this estimator object, we're going to use an MXNet object. Okay, this could have been a TensorFlow object. Okay, and what we're going to do is instead of giving this MXNet object the first-party algorithm, we're going to give this MXNet object some training script in MXNet. So it's going to be a Python script. Okay, and we'll see that in a second. So again, MXNet training script. This is what I've implemented from Glue-on-CB based on this research work being done in Berkeley. This is what the script looks like. It's purely Python code, MXNet code. First part of the code is actually just us building the architecture. Really complex GANs are really complex architectures, and these cycle GANs are even more complex. Okay, and if you want to talk about GANs later after the session, please feel free to come up to me. And then the last thing we're going to do is we're going to build some code for actually training the model. Okay, again, this is code implemented by Glue-on-CB, inspired by this work being done at Berkeley that I've implemented now in SageMaker to run it on SageMaker. Okay, and what's really great about this is I get this really high, very functional, very sophisticated architectures, and I can build custom models out of this. Okay, so this is what the code looks like, and I'll share all the resources for this at the end of the show, at the end of the session. I run my training job. Okay, and I've already run this training job. I won't lie, it actually took several hours to run. If I would have used CPU instances for this, or CPU power, probably would have taken a couple of weeks to run this model. Okay, so what we get as an output is going to be a couple of different objects. The main objects of this output, which I've downloaded from S3, the main objects of this output are going to be two different models, two different functions. One model is going to be able to transform horse pictures into zebra pictures, and the other model is going to be able to transform zebra pictures into horse pictures. Okay? Hopefully it will do that. That's what we're expecting the model to do. Okay, so let's take an example of our horse and zebra, of our horse to zebra model. Have some helper functions for visualizing the results. Okay. First thing we're going to do is we're going to take an image of 3 horses on a beach. And we are going to see what the model has to say about this image. Okay. And we see that effectively the model has learned to translate or to convert horse pictures, images, into zebra images. And what the model actually learned here is that the intrinsic differentiable functions or features here are the stripes, right? So the model has actually learned to draw stripes on the horse's hide. Okay? Let's go the other way around. How do we go from zebra images to horse images? We have a nice little smiling zebra here. Let's see what the model does in the transformation. And what you can see, again, it's not a fully performant model, but it's learned to hide the stripes on the zebra, right? So it's actually learned some really interesting behavior about what differentiates between a zebra and a horse. So I've actually created a GIF here of that shows you the process of learning of the model. Okay, so these are different iterations with time of the model on this picture of the zebras. And you can see that initially the model didn't know how to draw the stripes. Right now it doesn't even know how to draw stripes on the legs, but slowly it starts converging to an actual solution. And you can see that by the end of the training process, the model has learned to draw really interesting stripes around the horses. Yeah? I think that's a really interesting illustration of how the learning process works for deep learning. So let's look at another really interesting example. We're going to use the exact same type of algorithm, except now we're going to feed the algorithm images of French impressionist Paul Cézanne and real-life pictures. And what we're hoping to get is something that we call style transfer. Again, pictures of Paul Cézanne. Something that's called style transfer. You might have seen this in social media applications. There's something called filters, right? So the things that you get here is that we're going to be able to use Cézanne style on real-life pictures, and by the same token, we're going to get Cézanne pictures into real-life style. Okay, so let's see what the model is done. Now, again, we've trained the same model, same algorithm as before, but now we're feeding it images of French impressionist Paul Cézanne and images of real-life pictures. Okay, so here we have an image of landscape by Paul Cézanne. You can see that it has houses and a little road, as well as some trees. And let's see what the model has done. So you can see that the model, again, these aren't super performant models. They can always learn more. But you can see that it's actually attenuated the colors to more real life-like colors, right? It's given some texture to the trees, and it's also given some texture to the rest of the landscape. Okay, so I think it's actually done a really good job at trying to convert this oil painting of an impressionist painter into an actual real-life picture. Again, this is something I trained in a couple of days at my own at home, right? If you have time to actually do some research, you can get really interesting results. Now let's go the other way around. This is a picture of my beautiful wife. She went out hiking in the early spring. So a really nice landscape of mountains and trees. Okay, and we want to see how we're able to transfer the style of Zazan on this picture. So great. What we can see is that, yes, there is actually some type of style transfer, right? There's some artistic traces on the trees as well as on the mountains. And of course, the face of my wife has been blurred. So there is some style transfer. But now I think this is one of my favorite pictures. This is my wife swimming with some sea turtles. Okay. And what I want to see now is what the model is capable of doing with this image. And you see some really cool results, right? You see that the model has actually given some really artistic traces around the water. It's changed the color a little bit. It has some really trippy, dreamy kind of style. You can see around the turtle also, it has changed sort of the style into more of an oil canvas. And we didn't see before, but we did have this kind of two-dimensional texture going on with the picture, right? Okay, so that's for the demo. So what have we learned in the demos? We've actually learned how to build from an end-to-end process of building sophisticated deep learning models using first-party algorithms and bringing our own more complex code, right? The references for all of the work and all of the code being used here is available with these links. So thank you for having me. Please, if you have any questions specifically about deep learning, machine learning, and GANs, I'm always here for having a further conversation. Thank you again, and have a good day.